Room? Okay. So remember, what you heard and what the truth is for this class might be two different things, but let's go over this heat business. What's the symbol we have for heat?
Q.
Q. That's good. Q, or sometimes big Q, but we just talked about reaction quotient, so let's just keep it as Q. Q is heat. What's the symbol for enthalpy?
Delta S. No, that's it. Delta H.
Delta H. Good? And so the enthalpy, so sometimes when people say enthalpy, or sometimes when people say heat, they mean enthalpy. Most of the time when people say heat, they mean heat. So you need to be very careful about your use of when you say heat, which is Q, and when you say enthalpy, which is delta H. So a reaction can have a positive or negative enthalpy. If a reaction has a positive delta H, what do we call that? Endothermic. We have to put Q in, or we have to put enthalpy in to make the reaction go. If the enthalpy is negative, this is exothermic. And so this is the definition of an exothermic or an endothermic reaction. So the complicating factor is free energy. Is free energy heat? No. Delta G 0 is delta H 0 minus T delta S 0. So part of free energy includes the enthalpy part, but you also have this entropy part as well. And so whether you're putting heat in, whether you're putting heat out, you don't really need, this is not a state function, right? You can't say I put heat in, I put heat out, I know how the enthalpy changes. You want to stick with the strict definition of positive and negative delta H, and also what's going on with the free energy. And this won't lead you astray in terms of, is it exothermic or endothermic? So we talked a little bit about internal energy. Do we have any good equations for internal energy? What's the one equation we have? What's the symbol for internal energy? Delta E. What's the one equation that we have for delta E? Q plus W, right? So I said something on the homework about, I asked you that the internal energy of the products is higher than the internal energy of the reactants, right? Is this reaction exothermic or endothermic? Lots of people got it, endothermic, right? But I don't necessarily have to add heat. I can add work. Heat and work are interchangeable. So it's not necessarily true that I have to add heat for an endothermic reaction. I have to add enthalpy. But that enthalpy can be a combination. We don't have an equation that relates delta E to delta H. But if the internal energy is higher, that means I have to add energy somehow. So adding energy is an endothermic reaction. So this heat, energy, enthalpy thing, it can get confusing, and I'll try not to make it confusing on the exam. But watch out in your other classes, or when you're talking to someone on the street about enthalpy and exothermic reactions, make sure you call them out on their usage of terminology. And remember, you can't go wrong with these equations. This equation is always true. It will never not be true. There's no exceptions to this equation. Same with this. There are no exceptions. And so if you stick with the equations and learn how to use them, you can't be wrong. If you try and figure it out, oh, I just take some free energy from here, some free energy from there, that's hard to reason your way through. Is that good on exothermic and endothermic? Okay. Other questions? Yeah?
Can you go over the pH thing today again?
Sure.
Like, is that just a constant? the 1 times 10 to the negative 14th.
That's a constant. That's so we didn't do a whole unit on pH, but you should know how to use pH because it's a basic skill. So the KWW equation is 1 times 10 to the minus 14 equals concentration of H plus, concentration of OH minus. You just have to learn this like you know the gas constant. And so this tells you at neutral pH, what's neutral pH?
7.
7, right? And so the definition of pH is negative log of the concentration of protons. And so if you put 7 in here and solve for that, that tells you that at neutral pH you have 1 times 10 to the minus 7 protons, 1 times 10 to the minus 7 hydroxide, and that's why we call it neutral, right? Same amount of positive and negative charges coming from water. The reaction is this. Yeah. Right? That's what the reaction is right there. So the equilibrium constant dissociation of water is this, and that's where the KWW equation comes from, because this is liquid, aqueous, aqueous. What's the reaction quotient for this thing?
H plus concentration, OH minus
H2O is the solvent, H2O is the liquid, so it's not included. So this comes from the equilibrium expression for water dissociation. And so if you know this, well, if you know the proton concentration, you can figure out the pH. If you know the pH, you can figure out the proton concentration. Then you just drop that right into the KWW equation, and so you can move between hydroxide, proton, concentration, or pH, however you want to. So there's something called POH as well, but I'm not going to ask you about it, but just for your benefit. POH is negative log of the concentration of OH minus. Nothing fancy about that. Does that work for pH?
Yeah, he asked, yeah, that's POH, so you can't do it.
So if you know this equation, you can't go wrong with pH. Is everyone comfortable with entropy, delta S? Don't be afraid of delta S. You've been afraid of it before, right? Everybody thinks entropy is very confusing, but it's not. Are you afraid of delta H? No, you know how to calculate delta H, right? Enthalpy is very friendly. We kind of know what that is. Delta S seems to be mysterious, but it's not very mysterious because we have a couple of good rules to use. So how do we figure out the delta S0 of a reaction?
Some of the products minus the reactants.
Right?
Now, is that the same for enthalpy as well?
Yeah?
Yep.
Is it the same for free energy as well? Works for delta H0, works for delta G0. This works for all of our state functions, delta H, delta S, delta G0. So is the reaction the system or the surroundings? System, right? This is always the system. So we draw our diagram. System. Surroundings, where's the universe? Both of them. Universe. delta S of the universe equals delta S of the system plus delta S of the surroundings. What's the only equation we have to calculate the delta S of the surroundings? Yeah. Is negative Q system over T. So we have an equation for the entropy of the reaction or the system. We have an equation for the entropy of the surroundings. We have an equation for the delta S of the universe. We're all set. Those are the only 3 entropy equations there are. So if you want to calculate the delta S of the system, you better be using something like this, or you better be going to delta G0 equals delta H0 minus T delta S0, and if you know these two, of course, you can get delta S0 from that as well. Don't forget that approach. So we have an equation for that. We have an equation for the delta S of the surroundings. So if we know what the heat flow is, we can calculate the delta S of the surroundings, and then we know our rules about delta S of the universe. If it's a phase change, if it's not a phase change, etc. So entropy can be boiled down to these things. And you know, this whole what has higher entropy, water or ice? I mean, you know that. That's easy, right? Those are the quick ones on the homework. The long ones on the homework seem to be, how do I figure out the entropy of these different pieces? But these are the only entropy equations we have. That's it. So entropy doesn't have to be mysterious, just like delta G and equilibrium constant, if you know your way around the equations. Yes?
How do you do those problems where, say you have like a block of like 100 grams at like 200 degrees Kelvin, and then another one like at 100 and they touch? And
Yep. We'll get to that in 1 sec. Any more questions on entropy? Yeah.
Now, what's the difference between, I know you said that they have phase change,
Yeah.
and one that takes or gives heat?
Yep. So the delta S of the universe for a phase change is what? 0. The delta S of the universe for everything else is positive. Okay? So for a phase change, you